Hi, this is Vishesh. I'm going to be talking about Physics 2 Lab 3. So the overview for this lab. The purpose of this lab was to measure the magnetic field from a bar magnet to determine the magnetic dipole moment, to find the distance dependence factor, and find whether a bar magnet can be treated as a dipole or not. So we used the PhoneApp magnetic field reader to measure the magnetic field at various locations, and then we graphed this on a logarithmic graph to linearize our data. And we then found that the distance dependence from a graph, and we could use the Biot-Savart law to calculate the magnetic dipole moment from the graph as well. We use the app and experiment to find the magnetic field at a 45 degree from the axis, and then compare this to the actual magnetic field vector found by our coded computational model after we gave it the value of mu we calculated from the previous parts of the experiment. So some important themes for this lab. So we're going to be using the Biot-Savart law for magnetic fields, and that's shown on the right side. We can later simplify this to have an on-axis or an off-axis perpendicular equation. Then we have that B bar equation. That's going to be used for K, which is a constant, R to the power of N, which is our distance dependence factor. So then we'd also use logarithms to create graphs, which on the right side you can see how we graphed our data. And then an important theme is that orthogonal vectors dot product equals to 0. So the procedures for this lab. So we would orient the device so that the x-coordinate of the magnetic field is equal to 0, and this ensures that the readings wouldn't be affected by the Earth's magnetic fields because of our orthogonality and dot product principle. Lining up the bar magnet with the ruler, we then needed to find where the magnetometer chip was in the device, so this would be accurate for our magnetic field measurements. So when the reading spiked in the x direction in that first picture or in the y direction in that second picture, we were able to put tape on our device to locate that chip. And then we move that chip up or down the ruler to find lengths which correspond to the required magnetic field readings for that x coordinate. So some of the data for this on-axis part of the experiment. On the left side, you can see each distance correlates with a magnetic field reading, and then we have averages in blue, and we graph that data on the right side to create our logarithmic graph. And so we can see that the slope is going to be represented by n, and the distance, which is the distance dependence factor, and the y-intercept is ln of k, which we'll use to find mu. The slope was negative 3.2164, which is close to the value of negative 3 we're looking for. In the bottom right, you can see the Biot-Savart law equation with our distance dependence factor of negative 3 if we were to put it r in the numerator. So for the off-axis data, we were going to do something a little different. So the x and y components are both going to be acting on the magnetic field, not just the x-axis, because we're now off of a single axis. So the by sub Earth represents magnetic field at the origin, and so we're going to use that to correct by measured, so we're only getting measurements due to the magnet. And then we use the x and y coordinates to find b net, which is calculated from all of those components. So the on-axis calculations to find mu. So we have n and ln of k from our plotted data. Then we'd use the on-axis formula for the Biot-Savart law, which we can match k with its corresponding parts. And we'd rearrange the k equals equation to solve for mu, which we got of 1.257 amperes times meters squared. So discussion. So some accurate statements is that when the magnetometer is far away from the magnet, it measures a near zero magnetic field in the x direction. And as the magnetometer moves closer to the magnet, it measures our x component as the magnetic field increases. And this is because we have that inverse relation to the distance, so that as something gets closer, it gets bigger for b. If we hadn't zeroed out the x-axis with respect to the Earth's magnetic field, though, results would have changed because each time we measure, the x component would be due to a sum of the magnet and the Earth's magnetic field, not only the magnet's magnetic field. In the situation, a solution could be to use the cosine of the angle of the ruler relative to the direction of the 45-degree angle, because this would correct and only use the component due to the magnet. If we combine two magnets end to end, the magnitude of mu would be larger, though. So for the coding section, on the right side in the picture, you can see that we have the magnet in the middle, and then we have the vectors all around it. So on the left side, you can see we have the b-axis and b-perpendicular vectors we calculated, and then we have b at a 45-degree angle, which is also at a distance d away. So we have a different value we found for this vector than we calculated in the last part of the experiment, which we got at the bottom. You can see on the screen the values for that vector. And this is probably because of more accurate measurements done in the program since we're using the actual formula. And in real life, we could have had interference from electronic equipment around the room, which changed this value. So then we're going to look at the actual coding section. So on the top here, we have the constants defined, and we have a function here to find that b vector, which is def dipole b, and then we would find our vectors for b are on the on-axis and then perpendicular all around the magnet. Over here, I created a few more vectors at the 45-degree angle just to emphasize what it's going to look like, and we can see that in the general picture of it, we're going to have b vectors going out of the positive side, around, and then back into the negative side.